Hello. For today, I'll be talking about the concept of electric dipole together with Poisson's and Laplace equation. So, electric dipole. The definition of an electric dipole are two-point charges of equal magnitude but opposite polarity, separated by a small distance. So, you can see the figure here. So, we have the charges here. We have positive and negative charges with equal magnitude, and it's separated by a very short distance. So there are many types of dipoles that exist in the electromagnetic field. Uh, for now, we are going to focus on electrostatic fields. So when we look at a capacitor, capacitors are basically two plates which is separated by an insulator in the middle. So basically capacitors are dipoles as well. So we will use the knowledge on electric dipoles later to analyze the characteristics of capacitors. So now first let's derive. For an electric dipole, we want to determine the electric scalar potential V and electric field intensity E at any point P. So in this graphical representation, P is represented as this coordinate here. So we assume that the coordinate P is at a distance R, which is much larger than the separation distance D. Okay, so for us to be able to simplify our derivation process, we assume that the coordinate P is much longer or farther away. So the R here, the distance is much longer than the separation distance D here. So we are going to use spherical coordinates to represent the point P. And in order for us to derive, we go back to the equation on electric scalar potential. So for electric scalar potential, V, for point charges, now we have 2 point charges, positive and negative, and the magnitude is the same. So we have the equation as 1 over 4 pi epsilon naught, and then Q divided by R1 plus negative Q divided by R2. So we can simplify this equation to this form here. Now, we can further approximate this equation in terms of this value, R2 minus R1 and R1 R2. Since the separation distance is much smaller than the distance between the dipole to the point of analysis, the lines labeled R1 and R2, we can assume as approximately parallel. Okay, so we can assume the line here, since the distance is very far away, we can assume R1 and R2 are parallel. So by using this assumption or approximation, we can apply that R2 minus R1 equals to d cos theta. So if we assume that R2 and R1 is parallel, then the difference between the length of R2 and R1 is this portion here. And this portion can be determined by the trigonometric equation d cos theta. Furthermore, since they are approximately parallel and since the distance is about the same, we can assume that R1 and R2, because R2 is slightly longer than R1, but R in the middle here is, we can say, as the average between R1 and R2. So we can say that R1 times R2 is equal to R squared. So using these two approximation, we replace the value of R2 minus R1 here with d cos theta and R1, R2 here with R squared. So we get the equation V equals to QD cos theta divided by 4 pi epsilon naught R squared. To generalize this result to an arbitrary oriented dipole, that means now in the previous example, we put the dipole on the z-axis. But in actual fact, when we want to analyze, the dipole might not be on the z-axis. It might be on the x-axis, on the y-axis, or it may be in between. So we need to define an arbitrary equation that can represent any type of dipole configuration. So here we can derive the equation QD cos theta equals to this value here, QD dot AR. Okay, how do we do this? How can we derive this? Actually, we have to recall that from dot product, if we have a vector, let's say A, and we apply the dot product to a unit vector AX, we will get the answer as A cos theta. This one is from vector calculus. So now we can see a pattern here. Since we have d cos theta, so if we replace d cos theta here, we can represent it as vector d dot product with the unit vector. In this case, since our coordinate is in spherical, so we use AR, which represent the direction of the radius. So furthermore, we want to simplify QD here. So we represent QD as another vector P, where P equals to QD is called the dipole moment. So now we utilize this equation here and put it back into the equation for electric scalar potential. So we have this equation here. So this is the generic equation if we want to find the electric scalar potential for any dipole. Now, the next question is how do we find the electric field E? So we know from our class last week that we can derive E equals to negative del V. Okay, so the electric field is actually can be calculated by finding the negative gradient of the electric scalar potential. In spherical coordinates, this is the equation for gradient. Okay, this one is obtained from the table that I have shared with you when we studied about vector calculus, when we studied about gradient, divergence, curl, and Laplacian. So, we will replace the value of V here. We are going to use the value here, QD cos theta divided by 4 pi epsilon naught r squared into V here and differentiate. So for the first part, when we differentiate, we find that since we only need to differentiate over the radius r, so all the other variables become a constant, so we can take it out. And when we differentiate, we get the answer as negative 2 over r to the power of 3. Now we replace the same value of v in the theta component, and when we derive, now we differentiate over theta. So all the other variables other than theta, we take it out as a constant. And when we differentiate cos theta, we get negative sine theta. So because we have negative here, and we have negative from the original equation, so the negative cancel out. Now for AV, if we replace, inside the equation here, there is no phi component. So when we differentiate something without the component, we need to differentiate over phi, but there is no phi. So for the final part, the answer is 0. So we only have these two components. So now by using what we have derived, we simplify the equation to obtain this equation here. So E equals to QD divided by 4 pi epsilon naught R to the power of 3. And then we have this vector here. Right. So this is how we determine the value of V and E. Okay. As an extension, we also need to know about Poisson's and Laplace equation. Now, from Gauss's law, we know that the divergence of the electric flux density, del dot D, is equal to the volume charge density. So, since we already know that D is equal to epsilon E, we replace in the equation to get del dot E equals to rho V divided by epsilon. And since we already know that E equals to negative del V, we replace this value here in this equation here to get del dot del V equals to negative rho V divided by epsilon. So del dot del V, if you look at the definition, is equal to del squared V, which is the Laplacian operator. So in essence, the Poisson's equation states that the Laplacian of an electric scalar potential V is equal to the negative volume charge density divided by the electrical permittivity. Now, if the medium we want to analyze has no charges, then rho V is going to be 0. Hence, the same equation we will get del squared V equals to 0. And despite this is exactly the same equation, but one has a value and this one has a 0, it has separate name because it is derived by two separate people. So if we have del squared V equals to 0, it is called the Laplace equation. So what is the significance of these two equations? For the moment, we are going to skip on how to use this equation. But as a general knowledge, Poisson's and Laplace equation are useful when we want to determine the electrostatic potential V in regions with boundaries on which V is known. For example, the region between capacitor plates with a specified voltage across it. So when we come to the topic of capacitor later on, we are going to revisit the concept of Poisson's and Laplace equation. Right. So let's look at the exercise I have prepared. It's a short exercise just to make sure you understand the concept. So a dipole located on the z-axis with its center point at origin has a magnitude of 4 nanocoulomb with a separation distance of 5 micrometer. So you need to calculate the potential V and electric field intensity E at this coordinate. So notice that this coordinate is in Cartesian, but when we derive just now, it is in spherical. So you need to convert the coordinate first before you solve. So have a try and submit your results through ulearn. Thank you.